Hi folks, if you understood this powerful electrical engineering method, you can also apply it to many other areas. This motivated me to explain the mesh current method for heat flows, including all tips and tricks. So, what is today about? We keep finding analogies in different areas of science and technologies. The interesting thing is that we can reuse certain methods that we have learned in completely different areas. In electrical engineering, we know Ohm's law and also methods with which we can solve complex problems. It is Kirchhoff's rules from which the mesh current method is derived, for example. Today I will show you a few tricks and how you can use this method for thermal flows as well. And what's that for? Well, you can use the method to calculate, for example, whether it is worth installing thermal insulation on your house. In a previous episode, we developed a powerful Excel tool that can be used to calculate this and much more for an entire house. I linked the video on the top right, but today it's about better understanding how it works. Now, what is the analogy that I'm talking about? We know Ohm's law from our school days. And if you are in any way interested in electronics or electrics, then you have used it many times, I'm sure. The electrical resistance is simply the voltage divided by the current flowing through a resistor. And this means that if we apply two voltages, U1 and U2, to a resistor R, then a current I results from the differential voltage delta U divided by the resistor. Conversely, the differential voltage delta U can be calculated from the resistor R times the current I. Now we consider a thermal resistor RT. This could be a wall or a window. The inside temperature is T1 and the outside temperature is T2. If the temperatures are different, then a heat flow P flows through the thermal resistance RT. And it becomes bigger if the temperature difference is higher. Analogously to the electric resistance, we can also say here that the resistance RT is equal to the temperature difference delta divided by the heat flow P, or power flow P is equal to delta T divided by the thermal resistance RT. So if we want good thermal insulation for a house, then the thermal resistance of the walls must be high. Now, where do we get the thermal resistance from? Similar to electrical resistance, resistance can also be converted into a conductance G, which is simply the reciprocal of the resistance. We can do that with a thermal resistance as well. Then we get the thermal conductivity GT. For an insulation material, we can find the so-called U value in watts per Kelvin and square meter. We have to multiply this by the covered area to get the thermal conductivity value. The reciprocal of this is then our thermal resistance RT. Okay, using this we can now calculate the heat flow P that is lost through a wall or through a window. And why is it interesting? Well, this is exactly the heating power in watts that we need to apply to keep the temperature that we want inside the house. Or, to put it quite simply, it defines the heat energy over the year. The same applies to cooling when it is hot outside. The energy results from the power P in watts times the time period. This is how the heating energy is calculated in kilowatt hours for 1 year, for example. So we can predict the required heating or cooling energy. Okay, I think we got that so far. But now we have another problem. Of course, a house does not just consist of a wall or just a window. In fact, there are several interfaces to the outside, other floors, and to the earth ground. There are walls, windows, doors, the roof and false ceilings. And of course, they all have different thermal resistances. In electrical engineering, this corresponds to a network of resistors, exactly like in this equivalent circuit diagram. With the so-called mesh current method, all voltage differences and currents in such a network can be calculated. The same can now be done with the thermal energy flows and the temperature differences. For this, you need the so-called mesh impedance matrix, which you can then apply like an extended Ohm's law. Okay, we will see that in a minute. I will now show you a robust way to create the mesh impedance matrix. First, mesh currents are drawn as loops into the network in such a way that each resistor and each source is traversed by at least one mesh current. It is also important that we give each loop a direction. We will see why in a moment. With all mesh currents, it should look like this. For our example, we need 8 loops to cover all resistors. Next, we can start to create the elements of our mesh impedance matrix. For this, we introduce a principle that we follow. This helps us a lot not to get lost in the complexity. Each row of the matrix corresponds to a mesh loop. The first element of the first row is a diagonal element. For the diagonal elements of the matrix, we have to add up all the resistances through which the respective mesh current flows. In our case, we have RBI plus RB here. For all other elements that are not diagonal elements, we have to consider the mutual coupling of the mesh currents. There is no resistance between loop 1 and loop 2. Therefore, we enter a 0 for the second element of the line. The same applies for the third element. The mesh current 4, like the mesh current 1, also flows through the resistor RBI, but in the opposite direction. Therefore, we enter minus RBI for the fourth element. Loop number 5, 6, 7 and 8 all flow through RBI in the same direction as loop 1. That's why we enter plus RBI everywhere here. Our loop 1 also flows through the sources TO and TE. Through TO, it flows in a positive direction. Through TE, it flows in a negative direction. We represent this by the expression TO minus TE. Physically, this is the difference in temperature between the outside air and the temperature in the earth ground. We now apply the procedure to all mesh currents, i.e. to all loops, and thereby obtain the complete mesh impedance matrix. Here are 2 more tricks to check that we made no mistake. First, the diagonal elements of the matrix are always positive. Second, the matrix must be symmetric. And then I have to explain something else. The switches in our equivalent circuit diagram are also represented as resistors in our matrix. We find here the resistors for our 4 switches: RSB, RSG, RSF and RSA. If we want to simulate a closed switch, then we set the corresponding resistance to 0. For the open switch, we take a large value, like 1000 for instance. In this way, we simulate a switched on or a switched off heating. All the math for our problem now looks like this. If we multiply the mesh impedance matrix by the vector containing all heating powers, then we get a vector containing the temperature differences. In simplified terms, we can represent this in a matrix and a vector notation. Since we actually want to calculate the whole thing in the opposite direction, we have to invert the matrix. Then we can actually calculate the heating power from the temperature differences. And as we know, we then calculate the heating or cooling energy that we need over the year. Of course, that would be a bit tedious if every homeowner had to do this complex calculation himself. That's why we at Electronics Unmessed have developed an Excel tool for this. I will link at the top right a video under which you will also find the link to download it. Yes, it can be worth subscribing to the channel. So, this is what the tool looks like. It actually has many more features. Here I'm just demonstrating quickly how you can calculate how much heating energy savings the insulation of walls and roof as well as better windows and doors can bring. Note the gauge on the left, which always gives you the energy efficiency value of the entire house. In the top section here, we get the energy efficiency value broken down for heating and air conditioning. We have already entered the sizes of all boundary surfaces, i.e. walls, roof, windows, doors and false ceilings. If we now enter the U values of insulated walls, improved windows, etc., then with each improvement measure we see the improvement in the energy efficiency value on our gauge. If you are interested in the tool, it's best to check out the earlier video I linked to you. The insights. I hope you enjoyed the episode. We learned how to systematically apply the mesh current method to solve complex problems in a different context than electrical engineering. Maybe it will help you in your studies or inspire you to use analogies like this in other areas. I would be pleased. Just write me in the comments. Of course, with the tool mentioned, we will continue on the channel. Like I said, it's available for download. In one of the upcoming episodes, we will show a real renovation case where we have predicted the heating cost savings for insulation measures. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.